All right, good afternoon, people. Thank you for coming. Hope you've had a nice lunch. Um, there was shakshuka outside, so hopefully you appreciated that. It's very good. My name is Kedar. I've seen some of them are familiar faces. I've been tasked by NRF to lead this AI for Science initiative, and there are many workshops that have been planned. And sort of the idea behind this is culminating in July, which I will explain to you. But please do check out the website. And the website, it basically started with this question, right? So Hiroaki Kitano is actually one of the sort of the thought leaders in the space. He's run 4 workshops in this to this date, including in the US and Europe. And the idea was that can you actually, do a Turing test at a Nobel quality science activity? That's his vision. So he calls it the Nobel Turing Challenge. Um, I think our definition of AI for science is a little, perhaps, not necessarily Nobel quality, but a little bit lower level. So what we define AI for science, and this is a scoping report that some of you also contributed to, thank you for your effort there, is to solve scientific problems towards scientific discoveries, right? So can AI augment scientific discovery? That's what we call AI for science. So the focus is very much on the discovery aspect, right? And that's enabled through the AI. So what evolution needs to happen in AI, as well as complementary fields. So I think this is why all of you are here with hybrid compute and quantum computing. Can this help, to accelerate this process? Now we want to differentiate it, and please pay attention to this during the workshop today. Is that it's not science for AI or research for AI, foundation AI, which are method development in AI by itself, right? With no particular physics concept in mind, perhaps, right? So one good example of this is, they develop these equivariant networks, which are really good for symmetry operations in materials, and that would be AI for science. And you develop those further, and further development of those is very good for including doing materials discovery, right? So that's an example of AI for science. But foundational AI is like deep neural networks, and making them more resource aware, explainable, and so on and so forth, right? AI for X, we think, is a little more downstream, which is implementation of AI to solve practical problems. So take existing algorithms with data sets and apply it to improve productivity and things like this. So we are not looking for the bottom two. We are looking for the first one for this particular challenge. The way it's worked is that there are certain areas of interest for Singapore as a nation, which are top down, right? Health, for example, might be one of them. Climate might be another one. Hybrid compute could be another one. There's a lot of interest in this top down as well, and bottom up too, which are certain areas that are coming up. So I see some of you came for the physics complexity workspace. There's another one happening today on digital phenotyping. That actually came from the community, right? So it's a combination of these. And the idea of this workshop is to actually stimulate thought processes and define grand challenges in this space, right? So what we're working towards is this NTCI AI for Science conference. Please block the dates, 23rd to 24th July. It's going to happen here in Singapore. We've been inviting speakers from all around the globe, Microsoft Research, NVIDIA, and other top universities, Alan Turing Institute, etc. And we're going to do a 2-day workshop on this. But all of the thoughts that you've collected through these thematic workshops will be taken, and we'll task Dario to get your inputs to write a 3 to 5 page white paper, and that white paper sort of represents all of your thoughts, right? We could make this public, but we'll assimilate that information and put it in the full foundational research capability report. So this is what me and Professor Zhang Yang and NUS have been tasked with. And that report will be public facing. It'll be given to all the government agencies, to all academics, and internationally as well. So it'll be hosted on the NRF website, right? And that sets the stage for the AI for Science call for proposals, which is going to happen later this year. Okay. And through networking today, hopefully you can form teams and think about ideas that you can then form into some sort of concept paper for the call for proposals later. Right? So this is essentially the idea. Now, this is the website. Please check it out. You're also on there. We'll put some photos from our workshop today as well. We'll summarize all of this. We'll also have all the videos from today. They've been recorded, and that'll be uploaded at some point in the next month as well. What are the outcomes that we seek? So the vision statement. I think the vision statement for this particular workshop is a little bit in addition. So from NRS perspective, we want to separate two things, because quantum computing clearly is very valuable, right? So thinking about hybrid computing and quantum computing. So even if you remove the AI piece from it, we are also very interested in how quantum computing can augment science by itself, right? So please don't exclude this. Maybe Hans, who's from NRF here, would say a couple of words about what the thinking behind this is.
Thank you, Prof. Kedar. Yeah, first of all, I would like to thank Prof. Poletti as well for convening this excellent workshop and bringing the community together. From NRF's perspective, just to share a bit, we think that hybrid quantum computing could make some transformative changes in science, the same way that AI is poised to do so in the quite near future. We think that hybrid quantum computing in particular may be one of the accelerators of science, even in the NISQ era, before we achieve quantum supremacy. We believe in near term, hybrid quantum computing, including quantum simulations, quantum emulation, and similar methods, may yield some insights into science. So we've been looking, for example, at what the Prof. Alan Guzik from the University of Toronto has been doing with quantum chemistry. We've also been keeping an eye on how Japan is accelerating its hybrid quantum computing development and using it to accelerate science in tandem with AI. So we recognize that hybrid quantum computing is an entirely different thing from AI, but this is an effort, this workshop is an effort not to neglect the possibility that hybrid quantum computing can make valuable contributions to science in the near term and be quite transformative as well, even as AI is moving ahead to transform science. So as an outcome of this workshop, we hope that you'll be able to identify what are some of the bottlenecks in your respective fields where you believe hybrid quantum computing and associated methods may be able to make a difference, a transformative difference in science. So if you can identify what are the problem statements where hybrid quantum computing may be valuable, what are the bottlenecks towards solving these problems, and how can Singapore organize ourselves to best address these problems. In addition to that also, you could also think about what are your compute requirements. So I think NRF will be following up shortly with the community as well to get a sensing of what are all the entire community's compute requirements. Yeah. So yeah, I think as part of this workshop, if you can also help to address the question of how hybrid quantum compute might synergize with AI to make transformative differences in science, that would be very helpful. Yeah, thank you so much.
So there's a lot to ask, be asking from you, but please pay attention to these points, and then you can apply that to hybrid compute as well as AI and the intersection of them. I think that's perhaps the right way to think about this, right? So what is the vision? So please think big. What are the grand challenges in the field? How do we understand the challenges and the bottlenecks for these problems, and how we are specially placed to address these? Data, of course, comes up. Like, are you generating the data? What kind of data is needed? This is more an AI-specific question. So perhaps you don't need to address that if you're thinking about quantum compute, and about what kind of AI solutions come, which need to, is beyond what's available today, right? So transformative ideas, resources as well. If you need some compute resource, etc., please put those in your discussion sections, and we'll collect those thoughts. With that, I'll hand it over to Dario. Thanks.
Thank you, Kedar. Hi. Last few words of introduction. First of all, I would like to thank all of you for coming on a very short notice. I was informed less than 2 weeks ago to try to organize this workshop, but then I realized that Hans was going to help a lot on all the administrative matters, so he did a great work on it. And I was confident that the community, the quantum community, will respond quickly and excitedly to this. So I said, okay, let's go for it. I think we can do it. And so thank you all of you for coming here and be so positive. Now, can I have my slides, please? Okay. The title of the workshop was not chosen by me. NRF asked me to work on this. And then one of the things I'm going to ask you also is going to question even the title, okay, about hybrid and what do you mean by hybrid and whether hybrid is the right way to go. So we have people who work a lot on this, people who aim more for fault tolerant. So please come up with your perspective and share it with us. Thank you. Okay, so anyway, I'm Dario. For those who don't know me, Dario Poletti from SUTD and CQT. And okay, so when we think about, people think about quantum computing and AI, one of the things that comes to mind is to think about quantum computing, how quantum computing can help AI. And then, of course, there you can think about different primitives, the expressive power of quantum computer, the different optimization landscape, maybe even consider energetics. Okay, but and whether you're using classical quantum data, classical quantum algorithms, all of these things, right? Today, we can think about this, and I'm happy to hear more from you experts on this, but also would like you to think about the other way, which I think is the main thing of the workshop, how AI can help quantum computing. And this AI could be simply all classical. For example, how can he help the materials that we need in our platforms? How can he help really the platforms we use, or even help us to get better compilers or better algorithms and so on and so forth, right? In many ways, AI, classical AI could help. But then maybe if it's enhanced by quantum, if it can be enhanced by quantum algorithm or quantum aspects, then this can be maybe turned into a very powerful virtual cycle. Okay, so this is what I would like to hear from you. And as mentioned before, the goals that I've been told and also mentioned by Kedar just now, we define problem statements and set targets for potential hybrid or generic quantum computing for science, and enable or that work together with AI to make transformative advances. Understand the challenges and bottlenecks for these problems, and define how Singapore research community, which is you and a number of people who couldn't make it today or are online now, can best address these problems. So now we're going to go through some talks. Okay, we have 6 esteemed speakers that give their perspective on AI for science and quantum computing, both from academia and industry. Also, we have members of industry here, Horizon Quantum Computing, and also representative from Entropica, and maybe others I'm not aware of. And we will divide all of you in the second half in 5 tables, and I'll ask some of you maybe to lead different tables, and with a particular topic that will help form this document that we'll need to bring up to NRF later on. And so one table will be about applications mainly, and the other one about algorithms, bottlenecks, platforms, and local strengths. And I think like this, we can get a comprehensive picture. I will ask some people to maybe lead some tables. I already asked a few of you, and others, please join the table you think you're more interested in. Okay? Now, before we start with the first speaker, Jose Ignacio Latorre from CQT, I'm told that maybe a good thing to do is to pass around the mic and everybody just say their name and where they're from so that we know better each other. Okay? So very quickly, within 2 minutes, you will just go around and tell your name and where you're from. Ken, thank you.
My name is Feng Leong, and I'm from IHBC A-Star.
Yejun from IHBC A-Star.
Hi, I'm Tan Pui Han from A-Star Science and Engineering Research Council.
My name is Zbigniew Kalbarczyk. I am from University of Illinois, but we have a research center here as part of the CREATE program. So I'm here on the 14th floor.
Hi, I'm Adrian Mark from IHBC A-Star, Quantum Computing, Quantum Chemistry.
Hello, I'm Jian Feng from IHBC A-Star.
Dex from IHBC A-Star.
Pinaki NTU.
Kishore from IHBC A-Star.
Daniel from CQT NUS.
Hi, I'm Suminan from HTX.
Hadi from A-Star.
Bai Ping from HPC A-Star.
Hi, I'm Kilian from Entropica Labs.
Hello, I'm Patrick from CQT and NUS School of Computing.
Hi, Manas from IMRI A-Star and CQT.
Hi, JI from CQT.
I'm Joe from Horizon Quantum Computing.
I'm Stefan from School of Computing NUS.
Hippalgaonkar from CQT.
Hi, I'm Rahul Jain from CQT NUS.
I am Paulo from NUS School of Computing. Thank you.
I'm Kamalak from Chuan University.
Hi, I'm Gautam from SUTD.
Hi, I'm Feng Pan from CQT NUS.
Hi, I'm Chengran from CQT NUS.
Hi, I'm Wang Yong from SMU School of Computing Information System. Yeah.
Hello, I'm Terence from National Supercomputing Center.
Hi, I'm Feng from SIT.
Hi, I'm Rainer from CQT NTU.
I'm Kwek from CQT NUS and NTU.
Hi, I'm Long from CQT.
Marvin from NRF.
Hi, you're way.
Oh, hi, I'm Wei from CQT and NUS.
Wherever you want. Okay, you just arrived, right? You just arrived. Hi, can you see where you are?
Yeah, I'm Jianrong from NUS.
Okay, did I miss anybody? Oh yeah, there you are. Okay, thank you.
I'm Zian from CQT. Thank you.
Thank you. Missed anybody? Oh, we did this table already. Oh, yeah. Okay. Thank you very much. Thank you very much, everybody. So we go with the first speaker of today, José Ignacio Latorre. Thank you.
So thank you, Dario, for putting everything together. So as it was said, there is a lot of interest top-down on hybrid computing, and I think there is interest all over the planet. So NRF asked us to think a little bit about the challenges and definitely what could be an action plan for advancing in hybrid quantum computing. And what I did in the last weeks is simply talk to the places where they are trying to do something in hybrid computing, in particular in the supercomputing centers. So we had interactions with Riken, with Jülich, with other centers in Germany, with BSC, with and then we learn about Chineka, about Lumi, about what different people are trying to do. Okay, and the first, let me say very generically, the very first thing is that the subject, the idea of hybrid, has non-trivial lateral things, which are like that there is a strong commercial interest by some people. Okay, so there might be a lot of money there, and that conditions a lot what is a rational discussion in terms of science. So let me be very naive. So I will say very vague things. This doesn't seem to work. Thank you. The first thing I would like to make it clear is, at least from my definition, hybrid computing is not quantum simulation. Okay, quantum simulation is a completely different thing. The problem of quantum simulation, whether you can simulate quantum algorithms on a classical machine, this is very hard because we have a problem of memory, and you have essentially two options. And either you try to do it in an as exact as possible way, but this has a limit of, let me say, 50 qubits to give a number, or else you go to approximation methods that may be very good as tensor networks. This is already there in the community for many, many years. There is nothing, it's not new that we work in tensor networks. Whether then you need TPUs, you need GPUs, or what is the exact way you want to do tensor networks, well, maybe debatable, but it is not, in my opinion, hybrid computing, okay? Now, you may think that the supercomputing center should have some equipment ready for quantum simulation. This is absolutely okay. But the idea of hybrid, okay, to me is different. To me, the idea is whether we can combine the two machines working together on one particular problem, okay? It's different. Now, you see immediately this is not trivial. And the reason is that a large supercomputer are particularly good for dealing with large amount of data, but divided in so many units that everyone is doing some computation, which is, let me say, it's small computation. Okay, whereas a quantum computer is not good at uploading data. Because if you need to upload 1 million customers in your database, how do you do that? So actually, the typical examples that we all have in mind is Shor's factorization. Well, the problem is defined in very few bits. So it's a small data, very large, very intense computing. So this is the first idea, that what are the problems which are suited for a hybrid strategy? And this will not be obvious. Now, everybody quotes as an example of a hybrid attack the idea of using, for instance, variation quantum eigensolvers. So the idea here is that you do have a quantum machine that executes gates, but exactly which gates is described by a set of external parameters. Now you get a result, you check, and then you go through an iteration of optimization of these parameters. This was proposed a very long time ago by Alan and group and IBM. And it is well known that this problem, that the problem of this variation quantum eigensolvers is that maybe you're hiding the problem. Maybe solving a problem is difficult, but solving it with this technique may be as difficult because you don't know what are the parameters you have to put in your machine. This comes under the name of barren plateaus if you are thinking that you go through a minimization procedure to that. And there is no absolute evidence that we will get a real advantage, okay? There is a lot of literature, I would say, and I want to always to emphasize that these ideas were discovered when the computers were made. I mean, the first time I heard about this kind of problem was when I was in my PhD. So you have to go back to the 70s. Okay, at that point, people understood in the applications of condensed matter that you needed techniques such as the clustering approaches. So whether machine learning, artificial, I hope so, but I have some doubts, okay, myself. Now, I wanted to quote here the graph that all of you probably have seen from the papers of the first variation quantum eigensolver, but it is not mentioned that these eigensolvers were pre-trained classically. And only the last iterations were done on the quantum computer. So I wanted to take a picture from Manas. Okay, Manas has done an experiment, and this is a real experiment with real data that you try to train your machine. Imagine you go into the domain of hundreds of qubits, and you train. Well, this is terra incognita. You don't have any other technique. So you have to rely on the output of your quantum computer to do the training. This was done by Manas with the training. All data used for training were taken from experiment. Okay, and then things are not at all easy. You can no need to go through it. Very difficult to make sense. The errors add to a landscape which is itself very complicated, and it's very difficult to make progress. Now, let me go back to the idea of how to set up a facility. Well, the first idea is, why don't you have a quantum computer linked to a server, and you, from your laptop, you have a hybrid algorithm, such as the one that I was describing as the variation quantum eigensolver. Okay, so this is just to say that that this is easy, okay? And this is being set up now at CQT. And hopefully next year, that's a machine that will be run by the group of Rainer, who is here with us. So that machine will be accessible for all of us, and we will be able to run whatever you want to do as a variation quantum eigensolver from your laptop, and you can do iterations with a quantum machine. Now, to do that, I should say in advance that there is a mess, because you have to have a machine in a place, and there are firewalls, and we have been declared as a name that I've forgotten, as a facility that is that has to be protected in extreme. I don't know how to say that. So we are having now meetings with NUS, and they will make our life very difficult, okay? Because they claim that the quantum computer facility needs an extra security layer. So we will define an expert mode, and then we leave the general public for the future. We want to see how this can be encapsulated in the within the policies of NUS. Okay. This is to mention that, again, this is a problem. How quantum computers will be protected from misuse or from attacks. Again. Now, the next thing, and I think is the step that we have to focus, is that, as I will discuss in the next slide, the times that a classical computer work and a quantum computer work are very different. So there is a problem of synchronization and latency. So for that, you cannot use the classical computers as they are run on supercomputing centers now, that there are queues and you know, you send your jobs and they will run on queues. Okay, then you cannot do a hybrid computation. So what we are doing is something different. So we are taking at present 2 nodes from NSCC, and this has been done by our colleagues here at IHPC. Ji Jung has been leading this effort. And now these 2 nodes are now sitting next to the quantum computer by Rainer together. So now we link them. So you don't need to wait for anything. If you execute, you have absolute priority on both of them. And all the system is ready for you as a single user. There is no need to send queues which are peculiar. The system of queues for that is, again, supervised by IHPC, and it is being done as we speak. Okay, so people will go to the server, and the server will interact with the complete system. By the way, this is what I've seen happening in the supercomputing centers in the world. So what they are doing is that they are separating a piece, a bunch of the, in some cases, GPUs, in other cases, just nodes, for a special purpose use of the community of quantum algorithms. Okay, this is the only thing I've seen happening in the centers. Now, are there quantum computers in supercomputing centers? Well, yes, as you know, in Japan, there are, or in Jülich, they have a D-Wave machine, and they will be having a Pascal machine in this year. Are they fully connected at the moment? No, in Jülich, they are working independently. It's like having a separate machine. How they think for the future? Well, they think that a supercomputing center should be offering a diversity of machines, whether they are neuromorphic, whether they are GPUs, whether they are whatever structure you want to imagine. Well, quantum is there. Now, the interconnection is something that is declared that has to be studied, that nobody knows at this moment what is the optimal way of doing that. So let me go to the end by saying, what are the problems? Well, the first problem was largely debated. Co-location, yes or no? Do you need the quantum computer in the same facility as a classical supercomputer? That, if so, you call it co-location. If not, okay, they are separate. All the centers we have visited want to have quantum computers, so they want co-location, all of them. Okay, so the first issue is, are they together, yes or no? Well, many people want them to be together. You could argue that no need for that. You have 5G, so why should you have them together? Second is, what is the optimal architecture? What is it? Well, again, nobody knows. The way people are working is that they are making task forces to discuss this issue. Now, is each node accessing quantum computers, or all nodes access the same quantum computer? And if you have many nodes doing a piece of the computation, and at one point they need a QPU, how do you order? How do you organize these calls, and how you make the other guy waiting for the response of these things? So this brings the problems of synchronization. Okay, how do you make a supercomputing with many nodes to be synchronized with the quantum computers? Again, as far as I've been talking to everybody, I've not seen anything. Okay, I said and latency, and I mentioned security. So we discovered that this is a big issue. So many people are concerned how we protect a quantum computer. Imagine you have a super quantum computer that breaks all the cybersecurity. Wow, is that the same piece as the others, or you have to overprotect this machine? Okay. Now the jargon is starting to increase. So people talk about batch mode, about interactive algorithms, about integrated algorithms, about distributed algorithms, and then there are policies. As I mentioned, co-location has been discussed very heavily, and the HPC community that I'm aware of is all in favor of co-location. The argument is very easy. We are the edge of computing. We want to be the edge of computing in the future. So we need quantum computers. We cannot be away. There cannot be two facilities. Okay? Many people are interested in seeing whether quantum computing may not increase the speed, but may save energy. Okay? Can you generate some algorithm that you can prove that using quantum computing saves energy? That would be something. And everybody says that no matter what, they will support the local activities on quantum computing. So on top of, in Germany, on top of buying D-Wave and Pascal, of course, Barents is making his own quantum computer that will link also to that machine. So sovereignty is an absolute issue. You may not be the first or the best, but you have to be one of the players. Okay, and that's it. Let me say that I think hybrid computing is to be defined, is still in definition, and I don't see any way but bringing together expertise from HPC and quantum computer experts. I do think that hybrid computing will be implemented in HPC centers. I'm convinced by now. And I think it's a long-term bet, not a short-term bet. Okay. And the first steps, as I said, I've seen that developed in Jülich and Riken, and we are trying to set up a common effort to understand that better. I think this is it. Okay.
We are already a little bit behind time, but if there is a pressing question. Yes, one pressing question here.
How many calls? We are having 2 only now. But the plan for the future, yeah, we have to define. So one of the things is that we have to make a proposal now for the Aspire 2 system. How we want to organize this. Okay, so we will have a proposal and we will have something powerful.
Okay. Thank you, Ignacio. Okay, the next speaker is Kwek Chuan from CQT, NUS, NTU, NAE, anywhere else? Okay, okay, thank you. Singapore.
Right. I have 60 slides, but I promise Dario that I'll be quick. Most of it are nonsense anyway. So. Okay, so why do we consider about photonic integrated circuit, which is the topic that I'm trying? And the basic idea is that, well, between photons, there's of course the options of having electrons, and sometimes, in fact, we want both. So photons have a functional optical device that can be put on chips, and electrons, on the other hand, have transistors. Now, electrons are, of course, very small. So some of you have actually seen a lot of these slides. I've been recycling them a lot. Photons, of course, are massless. And so electricity, of course, very fast, but light move faster in some sense. Photons dissipate less heat, but there's a caveat. The photons need electrical heating for manipulation. And it's not just the speed of light. Electrons going through the copper carry limited bandwidth. This is not the case, well, in some sense, for photons. The technology of photonic integrated circuit was invented in the 70s. Right now we have somewhat in the industry, very well controlled high-speed rates as well as reduced power consumption. I'll skip that slide, skip this. Right now, one of the challenges of integrated photonic chip is linearity and non-linearity. And it is not so clear how we can incorporate that. This is, and we'll see about that. My take about the whole thing was started when we put everything of quantum communication on the chip. And so that was done some time ago. We imagined that we could harvest the photonic, the table of the benchtop and put it on the chip. Okay, maybe I'll skip this story. And the thing was whether we can put it on the mobile, but it's still a long way to go. I'll skip those. And I'll skip that. So how we started with photonic chips was started with quantum communication. We wanted to put everything that was on the box, which is not very big by now, because generations of advances have put the box smaller and smaller, but we want to put it on a chip. And so the idea was to have integrated quantum number generators also on chip, but that has been done. And by then, in recent years, we have decided that we could put it into other things on the chip, and that other things was what's called neural network. I'll skip this. So this was the how we in the past, like 20 years ago, we were looking at using computers to do neural network. And the idea, and of course, this was progress from rats to human. And the whole idea was that we look at laser auto-induced fluorescence, and we were able to use, in fact, neural network to classify the data. I think I have roughly a minute or so.
You can go ahead. 5 more minutes, no problem.
No, I'll skip. So if you want to know about some challenges, you can look at these references where they mention about convolution neural network can be done on chip, and diffractive neural network. Now, diffractive neural network typically is bulk structure. You make lenses, and the lenses, the diffraction lenses, mimic neural network. And you can have multi-layer matter surface system. And also you can have the last one, which I'll come back to it. So this is, we have demonstrated that you can actually do neural network on optical chip. And that was done quite some time ago. Now, in particular, optical chip has the advantage that it uses electric field. I mean, electromagnetic radiation is really electric field, and electric fields inherently are complex value, and we do complex value interference. Now, it turns out, of course, that in classical computing, complex value neural network was actually not exploited, and there were reports about how you can simulate better. So this is, I'll skip some of the results. And we have, of course, applied this neural network for computational chemistry. I'll come back to that, this work, because we have even refined that with boson sampling. So we combine, in fact, optical neural network with what's called diffractive lenses. And with this diffractive lenses, we are able to get some results, most of which is proof of principle. I'll skip this. This was done with Jose Ignacio Latorre. And what we did was to apply the photonic chips on for option trading, but basically it is a Monte Carlo simulation. So that it is made up of three parts: the loading, the payoff calculation, and a quantum amplitude estimation. This quantum amplitude estimation is only possible because of a particular encoding that we use at the input. And that encoding is actually unary, which was proposed by Jose in a separate paper. We have shown that you can also implement the quantum Franklin and Toffoli gate, albeit with some probability, but nevertheless, there were some nice results that we could show. I'll skip this. You can also perform cluster state error correction on the chip, and that was shown in proof of principle with cluster state. We demonstrate that you could actually get GAZ state. So this is the demonstration of the GAZ state. And as you can see from the diagram here, you get 0, 0, 1, 1. This is a complex part. The other part is the complex. So this is the real part, this is complex, the real complex. And with the GAZ state, of course, we demonstrate error correction on a cluster state. Well, you know about cluster state. More recently, we have also looked at how the Mach-Zehnder can be used as an autoencoder and see how much errors can be induced in such a circuit. And the result is going to be published later on. Boson sampling, there were 4 experiments that were simultaneously published way back in 2013. And the 4 papers by now are quite well known. But what exactly is boson sampling? Boson sampling just means that you have a unitary circuit that you implement on a photonic chip, and then you count the probability of various outputs. So in the case of 2 photons, trivial case of 3 inputs and 3 output ports, and you put a photon in the first and the third input port, then the output port can be 1, 1, 0, meaning the first, second, and nothing in the third, or 2 photons coming out from the second. And you can compute the probability. It's a very easy task for a small matrix. And then you can plot the histogram. Now, when you plot the histogram, that histogram can be verified with experiments. I can't forward for some reason. Yeah, next slide. Yeah. So this was the idea of boson sampling was first proposed by Scott Aronson and Arkhipov, Danny Arkhipov. And so this is the beautiful diagrams that typically you get out of boson sampling. And in this particular case, you have 16 modes, meaning that you have a 16 by 16 matrix, and you put 3 photon input, and you'll detect the output of the 3 photon. So various configuration can be obtained, and the top is the experiment, and the bottom is the theory. So you see some beautiful reflection symmetry. And by going beyond, those were 3 and 4, and in fact, 3, 4, and 5 has been performed. By having more and more input photons is extremely difficult. So an improvement on that was to use what's called the squeeze light. And with squeeze light, first proposed by Christine Silverhorn and Igor Zek. Igor was actually a CQT. You can actually go beyond the 20 photons limit. So with single photon, you calculate the probability of one of those configurations. It turns out that one of the probability of getting the configuration is in fact equal to the permanence of a submatrix that is composed of the input and output. And the difference, of course, is that with Gaussian boson sampling, you replace a single photon with a squeezed vacuum. And you also can calculate a version of permanence called a Hafnian. So that has been done experimentally with scatter short boson sampling, means Gaussian boson sampling, and at first it was for 12 photon, and the latest count it was a lot more, something like 40 or 50 photon. And the experiment has been done, but whether or not it has a quantum advantage is still a bit disputed. It can be shown, of course, that another application is that you can solve a lot of graph theoretic problems, and in particular, you can solve what's called the perfect graph matching problem. So with a graph, a particular graph, this is an 8 vertices graph, then you can always write the adjacency matrix. Now, with this adjacency matrix, you can try to compute what are the number, how many perfect matching do you have? So you consider any two vertices and how many possible ways you can pair them up. And in this particular graph, there are exactly 9, which you can compute very easily on a classical computer with Mathematica. And we did a proof of principle experiment for that, as well as a more recent one where we showed that you can actually solve various graph theoretic problems with boson sampling. So this I'll skip the details. And more recently this is work not published yet. It turns out that if you want to compute the probability of moving from one state to one vibrionic state to another vibrionic state, this probability is actually what's known as the Frank-Condon factor in quantum chemistry. And this Frank-Condon factor turns out to be proportional to the permanence of the submatrix. And with this result, we were able to demonstrate with a small molecule, you could actually compute this Frank-Condon factor. I'll skip the details. More futuristic applications. One can do, I think there is already an initial experiment on quantum convolution neural network. The one that is shown was a classical convolution neural network on a photonic chip. So this has not been done, and I believe it is. Okay, so this side. And one interesting application that I've been considering for some time is to fill up the fourth triangle. So we have the capacitor, passive device called capacitor, resistor, inductor. In fact, you can have what's called a memristor that links the charge to the flux. And this was first proposed by this guy, Leong, but it was not really demonstrated until recently, where HP Labs, I think, have done some work on it and show that it can be possible. So I'll skip the memristor. Other applications, I'm very interested in with the memristor idea to demonstrate what's called the van der Pol oscillator, the quantum van der Pol oscillator, in fact. And van der Pol oscillator has a classical phase space plot that looks like a diamond. And we hope that we can duplicate that with a quantum van der Pol oscillator. Another idea is to look into chaos theory. And it turns out that boson sampling can be related to some measures of chaos. Silicon photonic can also be used for agricultural purpose in the sense of sensors, LiDAR, infrared, and Raman spectroscopy. So thank you very much.
Thank you, Kwek. Still, also time for one quick question, pressing question. No, then we go to the next speaker since we're already a little bit behind time. Next speaker is Yechun, right? Is that correct? Yes. Thank you.
So, right. Maybe I'll use the slide.
I think it's back. I don't know. Yeah, thanks so much.
Okay, so I'm coming more from the angle of how does software algorithm and the middleware would be play in the hybrid quantum computing era. So I'm Eugene from HPC and also from A-Star Quantum Innovation Center, and also we are part of the National Quantum Computing Hub efforts. I think I will need this one. Yes. Okay. Yeah. So I think we always like to ask a few major questions when we are entering the new field. Why this is important? So to me, the importance of hybrid quantum computing is that we want to find a synergistic integration so that we can harness unprecedented computing power that to tackle the complex problem that we're facing in the world, both in terms of social problems or the economical problems that we want to solve. And we want to further advance our economy, our industry, for example, by having more computing power towards, let's say, how we can do better LLM with less energy, how we can do more accurate LLM, and so on and so forth. So for hybrid quantum computing, we are looking at something like this. So for me, I always like to think all the things from a more systematic point of view. So for any given system, we are looking at what are the subsystems that we're looking at. So for a hybrid quantum computer system, of course, we can decompose it into an HPC system and a quantum computer system and what's more important, interface system. Because we are facing the integration of very complicated system from both worlds. So for HPC system, we have relatively good knowledge about it because we understand classical algorithms. We have good understanding about how to process classical data, and also we have relatively good knowledge about how to use some of the classical system to do the control of the quantum systems. Well, for the quantum computer system, especially the people with expertise from the quantum world, especially our colleagues from the CQT, they have very good knowledge about what's actually happening below. Then, for example, this is the place where lots of magic stuff were happening. Looking at, for example, for when you execute a certain quantum algorithm over there, and also it has to be the place to perform the actual quantum computations. Well, then the problem comes, how to interface two worlds, where we have very different paradigm in terms of the computing, in terms of programming, in terms of communication. So that's the place where we are looking at interface system, where we're looking at, for example, how to enable better communication and better data transfer between classical and quantum instances. So let me further break down the system into different components. Yeah, this is a boring slide, I know. So starting with the HPC system, so maybe I give you some additional bonus. Yeah, this is some image that I co-created with DALL-E. So for HPC system, we're looking at normally a large cluster of classical composer nodes where they are interconnected with high-speed interconnects such as InfiniBand or TOEFL interconnect, where you can reach it's really good bandwidth in terms of the hundreds of gigabytes or per second, or even a few petabytes per second in the scenario of, for example, Fugaku. So to manage this kind of system, we will need something like the parallel programming models and also libraries, and also we need to have a really good job scheduler and resource managers, and also we have to have a good storage of the data. So yeah, I would say that this part of the story is more or less relatively more well known as compared to the web part of the story, where we're looking at the QC system. So that we already gained some knowledge about the QC system, where we're looking at, for example, the QPU design, a better understanding of the QPU performance via the characterization, calibration, and also all sorts of the tools to benchmark the performance itself. And also we have gaining good understanding about what are the peripheral system, like the cooling, especially the cryogenic cooling system to cool down the chip. so that we can shielding the noise from as much as possible. And also we have getting good understanding about control electronics, so that we have quite a number of companies out there who's trying to make money from building control electronics. And also there are people who are specifically looking at the specialized low latency interconnects in the, so that for example the wiring where you are connecting, how do you pumping microwave from outside, especially the control electronics, to the chip. So to do the control, to do the readout. Now, again, the problem comes about the interface. So interface will be the someplace where you have mostly in most situation, a classical computer, a classical workstation, running all sorts of things. And one of the important thing is the quantum compiler. I think Joe will have the best knowledge about it. And then we also have things like what are the things we want to do to program this monster over there? Yeah, especially for programming a QC system itself is already quite a headache. Then when we are, how about when we enter the stage when we are looking at the programming of this hybrid system? And then, besides that, we want to have interface with the applications. Then that's where we are looking at the APIs, libraries, and also how to do good integration between classical and quantum algorithms. And again, I think Joe will have some quite good insights from there, from his full compiler stack. Last but not least, how to do better job scheduling and orchestration tools, because this is extremely important because we have very different timing in terms of the timing of the computation for different type of instances. I will show you later on. So this is the place where I think the software, middleware, and also algorithm will play quite a number of roles. So for the interface system, that's a major place. And also we are looking at how to interface, how to have a good interconnect between the classical system with the quantum system via the control electronics. And then we are also looking at what are the some additional things, how to integrate, for example, with the parallel programming framework and also the our well-known job schedulers such as PBS Pro and Slim. So why this interface is important? I think this paper gave a very good insight, because if you take a very close look at the numbers over there, especially in terms of the bandwidth, the I/O bandwidth between classical and quantum instances, you see the difference. So it's dramatic differences, like a few orders of magnitude differences between the classical and the quantum. Even though quantum can do lots of things relatively faster, and also especially if you have really good algorithms that can speed up your calculations beyond quadratic, then you will still have some advantage. But that will require us to do lots of things. For example, we want to find more algorithms that has such kind of speed up. That is one. The second thing is that due to this kind of limitation, so even this one is already relatively optimum assumption theoretically, you are looking at the bandwidth is still an limitation. So normally we are only looking at a big compute and small data problems, not the other way around. So are there any problems that existing, for example, for the AI for science? So last but not least, as well articulated in that paragraph, we are looking at things far more beyond quadratic speed up. Now, let me enter into the more detailed analysis of how we are looking at this from systematic perspective. So we would like to enable this seamless integration and coordination between classical and quantum computing through advanced software and middleware innovations. Because we are dealing with complicated stuff, we have to make lots of automation in between, so that we can do better jobs in managing these complex system. And also there is an important aspect we have to do further software hardware design, where we want to further optimize our software design and also further optimize our hardware design, and of course, further optimize our interface design. So this is the general overview of what are the components that are needed for each cases. As I articulated earlier about the software pieces that can be further developed in terms of the HPC workloads, in terms of the communication and the coordination or orchestration, and the QC workloads for each different instances that we are facing. Now, I shamelessly borrowed these slides from our collaborator, Miyawaka Suji, who's heading one of the key projects under this JHQC program that has been just recently kicked off. And yeah, this is their perspective regarding how they are looking at the key middleware system, the key middleware and also system software they are trying to build up to support the gigantic Fugaku plus Quantinuum plus IBMQ system. So yeah, these are the components. These are the key components that are resonating with our schematics over there. Looking at the hybrid programming framework, looking at the API library building, and also they are looking at the job scheduling and orchestra tools. So of course we will definitely learn a lot while we are kind of collaborating with them. Then another following on the how question, then when we'll be seeing something going on. Yeah, for now we already seen things are happening. So in our RCCS, they are looking at the integration of Fugaku IBMQ, which is a 133 qubit system, and one continuous system, which will have 56 qubits. And also the other example is LRZ, where they are looking at, for example, integration with IQM devices. But how about what we would like to see in 5 years' time? Maybe we will be able to see more modular computing. We will see more better quantum interconnects, where the communications will become we'll go from classical to more quantum, and then maybe better error correction. So especially when you have better codes and also better decoding algorithms and can do things faster. And also and then maybe we are expecting to see the co-design of better hardware and better software, so that we can accelerate the process together with from both worlds. And last but not least, maybe tighter integrations. I think that has been articulated by GI just now. So we are looking at, for example, maybe co-location is one of the options, and on the other hand, whether on-chip solutions will be there. So, for example, the integrated photonics device from Kwek will be something useful to support this direction. Maybe beyond 10 years time frame, even though it's a slightly longer term, yeah, I think we can still dream about it a bit more. So, for example, maybe distributed quantum computing will become something feasible at that time, especially when we have more logical qubits that can work together with HPC. Then we don't have to worry too much about the loss of the decoherence. And then we can also looking at much more complicated, complex computations across heterogeneous cloud resources, like what we are currently seeing happening today, where we are looking at the heterogeneous structure composed by CPU, GPU, FPGA, TPU, and so on. Yeah, again, I shamelessly borrow another slide from our colleague, Miyako. And this is how our RCCS colleagues are envisaging the timeline from their project. So they are targeting end of somewhere around end of FY 2028. Yeah, somewhat 5 years down the road to build everything up. Yeah, so I think that can tally generally well with the prediction that I have just now. Now let's talk about our own perspectives. So this is how we are developing our strategy to focus on the end-to-end full software stack hybrid workflows and as an enabler, so that we want to achieve practical advantage via this streamlined process. So yeah, I will not go into the details about all these boxes, but you can see there are lots of the components that we have developed along the way. Then to support this workflow, we will have to have system design. So this is where the hybrid architecture innovation will come in. So we are looking at how to leverage the software techniques, AI techniques, to integrate the AI instances, the HPC instances, and the quantum instances together under one roof. And also we are looking at, for example, can we leverage HPC to do better work in simulating the quantum algorithms, or can we leverage HPC techniques to help with the design of to accelerate the design of the quantum chips? And also, can we do a better quantum compilation via HPC powered, for example, the mapping of the QP topology, and with all sorts of information going into the classical instances, we can do faster compilation so that we can get better execution of the algorithms on the real hardware. And of course, across all these things will be our ultimate goal towards the distributed quantum computing. Yeah, we are also actively exploring QC. So the first case is one of our examples where one of our recent efforts, we are looking at building up a hybrid CFD solver with one part of the solver, especially the pressure Poisson solver, offload to the quantum systems to deal with the linear system equations. While for the nonlinear part, we are looking at classical solvers to do. Yeah, so this is actually in collaboration with security and another and a major photonics QC company. We also explored a bit about the architecture itself, the hybrid neural networks, hybrid quantum neural network architecture itself. We are looking at how can gel QCN with classical neural network. I think you just heard Kwek's talk about the QCN. So this is one of our work showing that it can really help to predict the order parameters for the phase transition in this non-trivial many-body quantum system well. Then we do have active another very strong line looking into the classical shadows, where we are looking at where we have identified that, for example, when you have many shadows, yeah, even though the size of the shadows might be small, then we can look at how to leverage HPC to accelerate the post-processing specifically for these shadows. And this can be another avenue for us to explore the potential advantage by leveraging the HPC QC architecture. Here is one example from our team to look into the scheduling part of the story. So where we are looking at how we can better utilize the resources, especially the quantum resources. But of course, to enable this kind of scheme, we will look into very sophisticated control techniques, and also we want to have more. Maybe this is more applicable for the scenario, for example, such as distributed quantum computing. Last but not least, yeah, I think this this slide is a bit outdated. I updated a bit, and just I think I would just articulate verbally. So I think for the first one, we are looking at we are calling for actions in different places for the software and middleware design. So for software and middleware development, we are looking at, for example, especially for the quantum compilers, we do see a lot of strengths from the products from Horizon. So we are very looking forward to get a hands on that. And on the other hand, we are currently actively developing, collaborating with RCCS to look into hybrid programming framework development. We are also looking at build better and more classical quantum APIs and the libraries. For example, the hybrid CFD solver, hybrid drug discovery workflows, hybrid material discovery workflow, and so on. And also we are actively developing, contributing to the open source middleware development in QCH, especially in terms of the keyboard lab, and so on. And we would like to see further developments towards interfacing HPC and quantum computing by looking at the development of full stack hybrid platforms, and also looking at how to better optimize the task distribution and their optimization. And then we are looking at how to integrate well with our NSCC collaborators. So this is definitely in our roadmap. And also, I think the one next point is about the global collaboration. So I think this is, again, a very global activity. We would like to see more collaborations, more enhanced collaboration with RCCS. For example, we are planning to post our stuff out there to work closely with them on certain topics, especially around the hybrid programming framework and so on. And also we want to build better connection with RQC, and also we are also actively exploring collaboration with HPC centers with QC integration roadmap. One example is CSC, and there are quite a number of them that we can explore further. One interesting topic will be how we can integrate, for example, this effort together with our quantum safe network effort. So which tallies well with the, for example, can we go from classical communication to quantum communication to enable better quantum networks? And also we are looking at, for example, can we look into the joining some of the major global working groups such as IEEE Quantum HPC working group. So to make us globally relevant. And last but not least, talent is important. So we want to look into better quantum computing HPC skill trainings, and even the hybrid skill trainings, for example, via the platform such as NQCH Bootcamp, NSCC certificate training for HPC, and so on. And also, of course, we are there to support our ecosystem by supporting our startups, and also to by establishing public-private collaborations. That's all from me, and hopefully this is a good slide that convinces you that we should build this hybrid future together. Thank you very much.
Very quickly. Already thank you. It's a Hey, one quick question for you. No question. You later the discussion later this approach. Thank you. Next speaker is Manas Mukherjee from IRB Executive, and his talk is already on Zoom. And will be appearing here soon. All right, please.
Yeah, the screen. Yes. Okay, fantastic. 10+5 possible.
I will try, Dario, to 10+5. Okay, that's the number. Okay, so this is going to be very nimble because I'm an experimentalist, and what I'm going to tell you is very, very simple. We try to solve certain problems which are down in the stack, right? But maybe before I forget, this is our team. It's a research team. You can see the numbers, you can count them. And mainly I'm talking about the work done by Alex, who is on the left side, and Torun. Now, interesting thing is that Alex is my first computer science background PhD student. Yeah, that tells you like we are really serious on this. And what I'm going to tell you is more into what these quantum computers are based on. And in particular for us, it is based on an ion. On the right side is the ions level, and don't get scared. It's very simple from theoretical point of view because we remove all the levels and we only think of the two levels. We work with an optical qubit, which you see on the right side. On the left side is the harmonic trap. So you can forget about anything. It's a harmonic oscillator plus a two-level system. With that, I straight away go into what the topic of today is. So this package is built in-house, is made of the physics package, which contains the ion trap and the optoelectronics and detectors, which detect the state of the ion. Now, this optoelectronics, which you see here, is driven by these FPGAs, which forms the middleware. And then on top, what we heard about more complex things, HPC and so on, comes here. Now, of course, if you ask me naively, I would think this is already a hybrid because quantum computers standalone cannot work. It needs a classical computer to work. Yeah? Now, but that's not the hybrid I guess we are discussing here. A few things about our system. We can hold quite a number of ions. You can see the string from the trap. We can do gets 1 and also 2 qubit. 2 qubit gets are not that good. We currently work with a few ions only. Okay, now I would specifically talk about this, which we developed, which we implemented after GI and his group came up with this idea based on universal approximation that you can approximate any function just even in a single qubit. Yeah, that's the power of it. So, and that we try to utilize as much as possible. And that's called the data re-uploading algorithm. It's very simple. You start in this state 0, you upload your data with some weights, which you see here as theta and phi, and x is the data. And you create layers by these rotational gates. It can be of any dimension. And then at the end, you measure the state. And once you measure the state, you can classify by properly training it to one of the classes that you like to be. Okay, there are few inherent properties of these. And I'm not claiming here anywhere that there is a quantum advantage, because this is purely from mathematical point of view, there is no construct on the one-to-one to neural networks. And neural networks do not really tell you whether there will be an advantage. But this we have to do in practice and see if there is an advantage. And that's why we think it's a very good test bed for us. It gives you nonlinearity, which comes naturally into the system. And that's what we explored as well. So let me go not further in details, but because to this audience, probably this is very easy to understand. What we do in the QPU is mainly the evaluation of the cost. What we do outside in the CPU is the optimization. And that's a classical optimizer. I think what JI was pointing before, we did the initial training. on a classical computer because it's a very simple system, but then you use the validation with the real computer. And of course, now here comes the concept of hybrid. As mentioned, the classical computer does your optimization. I won't get into this, where we had actually shown that this hybrid system not only works for computing, but also for sensing. So we did some work on that. But what we are going to talk about is mainly on the implementation of a quantum classifier using the data re-uploading algorithm. And straight into the results. So these are some of the two-dimensional features that we showed that it can be done. These are all validation. Training was again done by the classical computer. What was more interesting after that was there is a photonic implementation which happened a year later, which you see on the right side. Now, this is the slide I'm again showing you. This is very important for us to understand the very basic principles where this particular type of system is difficult to train. And mainly because the hyperparameter space for this has a lot of minimas, which makes this get stuck at many different points. And we quickly observe this, that the top part, the blue curves, are the genetic algorithm. And it appears that if you use other optimizers like the gradient descent, at least the NISQ era system, it is very difficult to optimize or train them. And the reason being the step size or the resolutions are still large. So that's one thing which we have learned from it. Then going ahead, we looked into another aspect of things. While you train from any of these MNIST numbers, then you can actually attack it by changing slightly the picture. So you change the picture in a small way. I will show you how. And this work we did with NTU Computer Science. Initially we did with a PCA, which is principal component analysis. And of course, with principal component analysis, it's very easy to classify. However, they're very prone to any kind of adversarial attack on them. And now what I mean by the adversarial attack is that if you change the picture slightly, it would be falling from 98% accuracy all the way down to 54 or so. So with Anupam's group and his PhD student, we showed that if you change your picture slightly, which you see on the left, there's very little change. The accuracy drops to almost random. Okay, then what's next? We actually came up with the idea from, again, convoluted neural networks that we take the picture with its pixels. Then we fully use quantum algorithm here to use weightages, run each pixels with rotational gates, and then we combine them with the entire pixels and keep continuing doing it till we have a single number, and therefore classify the whole image. When we do this, it turns out to be quite robust against such adversarial attack. And in the same time, a couple of last week actually came up the extension of KN representation or network, which seems like very close to what we are doing. And there are certain advantages. I won't get into the details, but you can look into this recent publication from that group. What our result shows is that if you use this new convoluted classifier, you can actually protect quite a lot against you still keep the accuracy of the adversarial attack, as well as keep the validation accuracy quite high. I guess I will kind of stop here, except pointing out, if you look as we progress, the hybridization, if you like, happens at different locations. The first one was the optimizer, the hybrid system was here. But if you look at more recent work on the convolution, actually the hybridization happens even at the lower limit. So all our states that we are doing in loops are actually the rotation after it's projected. It is calculated in the middleware and feedback for the next run in here without going into the CPU. The CPU dials the overall change on the optimization itself. Of course, all these are home built. So all these, both the middleware and what we use, the architecture on the GPU are within the lab. Okay, so I believe I have convinced you. What we did was more related to classical data and quantum machine learning. We have also worked a little bit on the quantum data and classical machine learning. This might be more interesting for this audience as well. So we did train our data with a classical neural network, and I won't get into the details, but we do see that the neural networks are not as good for predicting the quantum results as we see. Okay, with that, I close. I hope I maintained 10 minutes.
You're faster. Fantastic. All of that was scary. Thank you, Manas. Okay, we can have time for questions for Manas. Question? Maybe about this robustness to adversarial attacks.
Yes.
I think this was more from, it's the way you implemented the algorithm on the quantum machine. Is there something like intrinsically quantum that helps to be more robust against adversarial attacks, or is like, the way you are thinking of the code and it can be implemented easily on a classical neural network?
Honestly speaking, we don't know why is it robust. However, we think it's because of the convolution we are doing at the pixel level. We using the quantum machine is this is the same kind of robustness you would get in a convoluted neural network, possibly, but we're not completely sure on this. Yeah.
Okay, so we go to the normal person. We go to the next speaker. Thank you very much. Thank you. Next speaker also on Zoom. I mean, he's here physically, but the talk is going to be presented through Zoom. Feng from CQT, NUS.
Hi, hello everyone. It's my great honor to be here to present some of our thoughts on AI for science and hybrid quantum computing involving generative models and quantum circuits. So I'm Feng Pan. I come from the CQT NUS as a postdoc research fellow. So today's talk will be mainly divided into four main parts. The first one is the main research direction of our group, which is the quantum algorithm for machine learning. And then I will talk about my own experience of modeling the Boltzmann distribution using the variational framework. We can use several variational ansatz to represent the Boltzmann distribution. If we use a neural network representation, that is approach of AI for science. And if we use a quantum circuit as a representation, we can see it as a hybrid quantum computing algorithm, which fits very well for today's topic, I guess. So my postdoc advisor, Professor Patrick Ribbentrop, is known for using quantum algorithms to enhance classical machine learning algorithms. This is two of his major works. The first is the quantum support vector machine, and the second is quantum principal component analysis. The key idea here is that if we have a fault-tolerant quantum computer, we can demonstrate a very good speed up for these commonly used machine learning algorithms by encoding the quantum data into by encoding the data into the quantum states and then performing carefully designed quantum algorithms onto them. And recently, we have our group have also figured out how to embed a transformer layer into a quantum computer by block encoding all these input data and also the parameter matrices into unitaries. And then by carefully designed quantum algorithm, we can perform typical transformation like the self-attention, like the layer normalization, and also the activation function onto these embedded unitaries. And then one could also pursue a potential quantum speedup in the parameter regime look like this. Okay, then I will talk about my own experience of the AI for science and hybrid quantum computing. So the task here is to modeling Boltzmann distribution. I came from the statistical physics community, so Boltzmann distribution is the most important research object to me. And it is important because it basically describes what equilibrium means with a specific energy function EFS. Here, Z is the partition function, which normalizes the Boltzmann distribution. And the most important physical observable will be the free energy F, because with the free energy, we can calculate all other observables in polytime with respect to the system size. Also, since that Boltzmann distribution is so fundamental, if we can accurately model in the Boltzmann distribution, this could lead us to many solutions of many scientific problems, like the probabilistic graphical models in machine learning, and also combinatorial optimization problems, and the decoding of quantum error correction codes. So we will use a variational framework to modeling the Boltzmann distribution. The key idea here is that we want to use a variational ansatz Q theta of S to approximate the Boltzmann distribution P of S by minimizing the distance between them. We will use the Kedar divergence as the target function. And if we expand the Boltzmann distribution, we can see that minimizing the Kedar divergence between these two distributions will be equal to optimizing the variational free energy FQ, and the lower bound of this variational free energy will be the exact free energy F as a constant. So if we want to do optimization towards this variational free energy, we need to calculate the gradients with respect to the parameter set theta. So if we reformalizing these gradients, we will find out that these gradients actually composed of three main parts. The first one is we need to draw samples from the variational distribution Q theta of S, and then calculating the expectation value. And the second part is what we call actual gradients, because we need to calculate the log probability of these sample bit strings to perform the optimization schemes. And the third one is what we call the score function, which is basically the energy function plus the log probability divided by the inverse temperature. So in reality, we can definitely not calculate the expectation value. So we usually approximate the gradient using the sample average. Here we have all the framework, but we also need to choose suitable variational ansatz, which should possess two important characteristics. The first one is it should allow us to draw samples from the variational distribution easily. The second one is that we need to have the ability to calculate the log probability of these samples in a reasonable amount of time. So the first variational ansatz will be the neural network. Back in the 2018, we had realized that it is not a good idea to parameterize the whole joint distribution Q theta S. Instead, we should decompose the joint distribution into products of conditional probabilities, which means the variables in current positions depend solely on previous ones. And modeling these conditional probabilities seems to be a better approach. This strategy gives us several advantages. The first one is the conditional probabilities is easier to model and to optimize. The second one is that these conditional probabilities give us a natural way to sample, which is called ancestral sampling, meaning that we will sample firstly the first variable, and depend on the value we sample from the first variable, we will get the second variable, and so on and so forth. The third one is that, remember, we need to calculate the log probability. Here, the log probability can be easily calculated. It's just the sum of log conditional probabilities altogether. So models that follow these so-called autoregressive property is called autoregressive models. And we can carefully design the neural network architecture to make the output of the neural network follows the autoregressive property. It also was mentioning that this autoregressive property is also the key to the success of current large language models, because it mimics the human speech patterns, which means our next words will usually depend on our previous words. Like when I say one sub home, you will know that the third word will be a, and then the fourth word will be once upon a time. So many studies have shown that these autoregressive models is very good at modeling the Boltzmann distribution. For example, in our research in 2021, we show that it can actually models the Boltzmann distribution compared to other heuristics, and also specifically in the rugged energy surface ones. And also because it gives us ability to modeling a Boltzmann distribution in any finite temperature. So we can do annealing to this to the Boltzmann distribution by gradually changing the temperature during the training process. So in the second Nature Machine Intelligence paper, the authors has demonstrated that this framework is better than the simulated annealing and simulated quantum annealing approach, because basically it gives us the ability to annealing the whole distribution, not just part of it. So, and the third one will be if we have the ability to modeling Boltzmann distribution at any finite temperature, we can annealing the temperature into zero, which basically means we can have the ground state of the energy function. This will give us the ability to solve combinatorial optimization problems with a specific ground state. So here in this year's NeurIPS paper, the author shows that using this autoregressive model, we can have a better solution compared to other heuristics in some kind of combinatorial optimization problems. Then this neural network representation can be seen as an AI for science approach. And we can also use quantum circuit to encoding this distribution by encoding the whole distribution with the ground to the ground state, to the final state of a parameterized quantum circuit, C theta. So in that way, will give us a hybrid quantum classical algorithm to model Boltzmann distribution. So quantum circuit is by nature a probabilistic generative model. And if we use this to represent a variational distribution, it will give us several advantages. The first one is unbiased sampling. The second one is faster sampling speed, because for the current superconducting qubits, we can sample from the quantum circuits very fast. And third one it will be that it will give us highly entangled variables. And then we can sample from the quantum circuits. But remember that we still need to calculate the log probability of these samples. That's where the classical computation involves in. So we will maintain a classical surrogate of the quantum circuit and do classical simulation to get all the sampled bitstream amplitudes through the classical simulation. And then the following optimization schemes will also executed inside of the classical surrogate. And then the classical surrogate will tell the quantum hardware how to optimize the variational parameters inside of the variational quantum circuit. So you may wonder why we need to do the quantum sampling if we already have a classical surrogate and can simulate it. So the key point here is that it's due to the computational complexity. So remember, imagine that we have a quantum circuit with n qubits and d depths. For 1D case, the complexity of classical sampling of quantum circuits plus classical optimization will be O(n) times 2 to the 3D. But if we have quantum sampling and classical optimization, the complexity will be O(n)d plus n times 2 to the d. So for shallow circuits with log n depths, this will give us polytime simulation and a quantum speed up in sampling. For circuits with 2D and more complex structure, even though we don't have systematically complexity analysis, the key idea here is that a classical sampling of quantum circuits is strictly harder than the classical simulation of quantum circuits. And my previous work of using tensor network to simulate quantum circuits give us good enough approach to get bitstream amplitudes in a reasonable amount of time for medium-sized quantum circuit. Also, I have recently launched a collaboration with NVIDIA to utilize a GPU cluster with thousands of GPUs to simulate quantum circuits, which can potentially speed up our previous approach by at least 10,000 times. So with that advancement, maybe it can give us ability to simulate all existing quantum hardware in the world, including IBM ones, Google ones, and QRO ones. Also, we have prepared the demonstration, proof of concept demonstration to utilize this quantum sampling classical optimization framework. We can see that the free energy can be optimized to its lower bound, which is the exact free energy, using these very simple circuits. Also, we have collaboration with IBM to implement this quantum sampling classical optimization framework onto their 127 qubits hardware. Okay, that is all of my talk. Thank you for your attention.
So we have time for questions.
Sorry.
Oh, yes, sorry. Thank you.
Hi, thank you very nice. I have two quick questions.
Yeah.
One is, can you extend it to Bose-Einstein or Fermi-Dirac distributions?
Yes, I guess so.
And the second is that, so what you at the very end, what you said is that you can emulate a quantum algorithm on these GPU clusters. Is that right?
You mean the hybrid quantum computing approach, right?
Right.
Yeah. So, so here will be two parts. We will have two parts to implement. The first one is sampling. Right. This is done by the quantum computer. And the second one will do some optimization by calculating the gradients. In that way, we'll need to calculate the log probability of these sampled bit strings. And then this part is done by the classical computer by classical simulation of this quantum circuit to get these probability amplitudes, and then do the optimization. Yeah.
Okay, thank you.
Thank you.
Thank you, Dr. Okay, last speaker for today is Joe Fitzsimons from Horizon Quantum Computing, and his talk is coming up soon. Thank you. I'll leave it to you.
Thanks very much. Is there a remote? Okay. Thanks very much. Okay, so I guess we've heard a lot about hybrid quantum computing today, and I guess I saw the acronym HQC used a lot, which I'm not sure whether to be terrified by or elated by, given that our company is called Horizon Quantum Computing. And when I got the invitation to talk, was phrased as talk about hybrid quantum computation and AI, and that's complicated for us. So this is going to be a bit of a grab bag of different activities we have going on at Horizon that relate specifically to these topics. So let me start by telling you what we're doing. So you can't see it here because of the Zoom bar, but it says at the top of the screen, programming quantum computers is hard. And programming quantum computers is hard for a number of different reasons. First of all, the quantum algorithms are non-intuitive themselves to construct. Variational algorithms, the kind of things people use on near-term systems, where they're just tweaking parameters, training them with stochastic gradient descent or something like that. Yes, they're very, very easy to work with. All good? I think just leave it. It should be fine. You can put it up the top. Okay, so it's so generally the variational algorithms are generally easy to work with, easy to develop for. There's libraries of them already, but there's no provable advantage for them. And if you ask me, there's almost certainly not an advantage for these variational algorithms for the vast majority of problems. I don't think we're going to be solving real optimization problems using variational techniques anytime soon. The hardware is also very imperfect and quite diverse. So you have all sorts of different architectures from, kind of standard gate model stuff that you see with superconducting qubits to other kinds of systems where there's measurement-based computation going on. For example, we've heard about boson sampling earlier, but there's all sorts of different techniques that are being used to try to build quantum computers. And then the programming languages at the moment lack abstraction. So it's difficult to write very complicated programs of the kind that you are likely to need to be able to tackle real-world problems. So at Horizon, we've been pursuing a plan to go all the way from classical computation to quantum computation. And what that means is basically taking in a classical program, something written to run on a conventional computer, being able to automatically construct a quantum algorithm out of that, then being able to turn that into a concrete description for a quantum program, compiling that all the way down to target hardware, down potentially to the pulse level, deploying on hardware, and then returning the program, the compiled program, deploying it as essentially as an API so that it can be integrated into whatever application is being developed. So this is really a chain for developing the quantum backends. When I talk about going from classical computation, at the moment we have standalone kind of tech demonstrations that work with a subset of MATLAB code that can automatically generate quantum algorithms from that. But that's in kind of standalone at the moment. And then below that, we have a chain that goes from a kind of high-level programming, quantum programming language we have, which we call Helium, which allows, it's kind of like a quantum version of BASIC, but it also allows you to include subroutines written in C or C++ that get compiled to highly efficient quantum circuits, so you can evaluate them on coherent data as well. Within those languages, we can compile down all the way to target different hardware across multiple different kinds of systems. At the moment, we have the system set up to run on IBM hardware, Rigetti hardware, IQM hardware, Oxford quantum circuits, a bunch of different system types. And then we're able to deploy these as APIs at the end. I'm going to start by showing you the standalone part for the for algorithm construction, kind of what this looks like in practice. Normally, when I show this off, I have about 40 slides that show the line-by-line changes that happen as the code gets automatically refactored. I'm not going to do that here. I'm just going to show you the initial piece of code and the final result to give you an idea. And the important thing I want to highlight here is that this is entirely classical code, and what we're going to get out at the end of the process is a hybrid algorithm. So it will run between a classical computer and a quantum computer. It's not a single quantum algorithm at the end of the day. It's going to have different components that run on different systems. So what you have here is an optimization algorithm I wrote in a subset of MATLAB. What it does is it takes in a function f given as a function handle, and between it tries to optimize it between the range of lower bound and upper bound for the input, where the input dimension is given by dim. And the way it's going to do this is it's going to expand a grid over that space. There's grid points, different ticks on that grid in each dimension. And it's going to look, it's going to find the minimum point on that grid across the entire space. And then recursively expand a finer grained grid around that until it has completed round number. The variable at the end, rounds, is the number of times to iterate. So you can copy and paste this into MATLAB, run it now, and it will work. The main thing to keep in mind is that this is going to work. It's going to find the global minimum whenever you have a bandwidth limited function. So if the grid points is chosen fine grained enough, so it gives you a kind of nice way for finding a global minima with a promise on it. The only difficulty is that this scales exponentially with the dimension. So if we put this through our system, what's going to happen? Basically, we'll start to eliminate the intermediate variables like lattice points. We're going to break apart the inner loop here. This inner loop will get fissioned into 3 different loops that stand alone. It starts eliminating the intermediate variables in those, replacing them, and then we'll fission the outer loop until it's broken down into very simple elements, and we'll replace each of those elements with a more efficient way of doing the same thing if it knows how to do that. So when you put in this code and you run it through the system, what you get is this. So you get this new program out where the parts highlighted in green, this is a call to a quantum algorithm that specifically finds local minima, but that quantum algorithm requires the evaluation of classical code within it. So this, as I mentioned about being able to compile code written in classical languages to efficient quantum circuits, that's kind of a necessary part of this step in order to be able to deploy it on quantum hardware. But the net result is that this is significantly faster than the previous algorithm, in the sense that there's a square root speed up on this, but because the whole thing is an exponential time algorithm, it's exponentially faster than the original algorithm. Okay, that's kind of our algorithm synthesis where we stand at the moment. And I guess you can see the output of this is a kind of hybrid algorithm where the parts in green are to be run on the quantum computer and the rest is run on a classical computer that is calling that quantum computer in the background. So we need a way to be able to express these programs on the quantum computer, to be able to read in data, to be able to evaluate classical code as part of it, and so on. So that brings us to our Helium programming language. And Helium is basically, it's an equivalent of BASIC. It has the same flow control of BASIC, but it allows for quantum operations rather than classical ones. So the building blocks you have are things like the ability to define qubits, or quantum systems of any dimension, to be able to define them to arrays, to be able to do, I don't have any examples of it here, but you can also do concurrent classical arithmetic. So if you have classical calculations that are fast, that happen to have the same time, then this can be expressed within the program. Alongside that, you have things like loops, you have subroutines, and it's Turing complete. So you can do while loops and things like that. You're not necessarily expressing just a circuit. It also has these two hooks, input and output, that will allow it to connect to external systems. And that might sound a little bit strange in the context of quantum computing, because I haven't yet talked about how this is implemented down at the hardware level. But basically, we compile this down to our own assembly language we call Hydrogen. The assembly language has a block structure, so it basically executes one block at a time and then decides based on a classical condition of the control system which block to go to next. So this allows it to depend on intermediate measurements, for example, but it also allows us to read in data from external data sources. Of course, there's some issues then about, can you keep the quantum data alive for long enough to do that? And at the moment, the way we implement this is that we hide it all behind the scenes, in that we run multiple times with post-selection so that we can match up two separate quantum computations as if they were a single one, to allow for data to be kept alive for a long time. Okay. The other thing I should say that's not shown here is that in Helium, you can also import files. So if you include what we call C to Q files, they allow you to describe a way to construct a quantum subroutine from files written in either C or C++. And that will be compiled into a set of Toffoli gates, CNOT gates, or whatever other gate set you're targeting. Okay, so we kind of see this as a good way for developing hybrid programs, in that it allows you to hook into classical compute resources. It also allows you to express the fast arithmetic that you want to happen to do, for example, things like decoding on FPGAs right beside the QPU, but also to be able to include more complex structures in your algorithm. For example, when you want to do something like options pricing and you want to express the formula using C or C++ or something like that, it allows people to develop complex classical computation using existing tools rather than reinventing the wheel. This is all integrated into our IDE and compiler suite we call Triple Alpha. So basically, you can write your programs in either Hydrogen, our assembly language, or in Helium, this higher level language. You can compile them down to target different processors. It's very easy for us to add new processors. You can see a list of some of the ones we have set up, both trapped ion and superconducting systems, as well as some simulators. You can compile down, hit deploy, and that will set it up to run on hardware. Our view as to what is necessary to actually make a meaningful a meaningful quantum program is a little bit different than what's done in essentially all other frameworks. So for us, it seems the endpoint of application development should be a deployable application, or in our case, the deployable quantum backend for an application. So it shouldn't work only once. It shouldn't just write the program, execute it, and then you're done, give your results. Instead, what we should have is we should have the program essentially living behind an API. So you can call that API, you can specify inputs to that API, it will execute the program on hardware, and then it will return results to you. And actually, there's 3 different times we can put data into the programs. So we can put in data at compile time, so when or at development time. So in our initial program, we might include some data that we're going to use within our program, but we may also want to use the same algorithm on multiple different kinds of data, in which case we would have used the input keyword to be able to read it in not at the development time, but instead when the API is called. So it's going to expect to see that data passed to the API in JSON when the API is called. Then there is one other time though. So I talked about including data at development time, including data at call time when we call the program, but we may also need to call it at runtime. Like we may need to insert or read out data during the computation. And you can do that too. So the system will wait for any data it has not yet received. So if you have a loop that requires it to do some quantum things and then read an input, unless that input can be pushed straight to the start or end of the computation, it's going to execute part of the quantum program, and then it's going to look for the input through the API and wait for that, and then you can update your inputs. You can provide the extra input, and it will continue further, and so on. And actually, I gave a talk at the APS March meeting this year and showed off a REPL we had built with this, where you could interactively, you could interact directly with a quantum computer, specifying kind of one gate at a time. It would execute on the system and would essentially continue your program as you went. So you could specify which gates to apply. It would keep executing the program. You could read out a qubit, and it would continue with all of that in place transparently. And importantly, of course, you could do this if this was your end goal. You could develop this yourself. You could write all of the code with Python scripts and so on. But for us, it's just a case of putting an input, marking a variable for input each time through a loop. So it's natural in our system. It's not a special case to be carved out. Okay. The other 2 things I wanted to touch upon is that we have announced we're setting up a quantum hardware testbed just down the road behind MediaCorp. We're extending our space by about 3,000 square foot. We've capacity for 3 quantum computers. We've announced the first one at this point, but it's a multi-vendor setup. So control systems are coming from different vendors than processors and so on in general. We'll be integrating with our software stack, and we have our own DGX H100 GPU server that will be connecting directly to it as well. That will allow for tight integration between classical computation and quantum computation. We've announced the first system so far. It's a modular design. We have control systems from Quantum Machines based on the OPX 1000. We have a Rigetti Nevera 9-qubit processor as our first processor, though we have capacity for multiple QPUs in the fridge, and we have an upgrade pathway to 84 plus qubits. So that's kind of where we stand today. It's going to be a little while before we get to our second system. Construction should start on the facility in the next week or 2. And we should have the first system up and running early 2025. The last thing that I wanted to touch upon is very different in nature, which is to tie in with the AI theme. A lot of the tools I've shown you have been inspired by work we had done. Actually, Patrick was involved in the original paper back when I was still in academia. We were looking at whether you could create a recipe for creating quantum machine learning algorithms, and whether you could take the tricks that are used to do fast linear algebra in quantum algorithms and make them kind of create a toolbox where they can be systematically applied. And since what we've done at Horizon has gone a different direction, we've put a lot of effort into creating quantum algorithms to navigate control flow in a more efficient way and so on. But this is all in the direction of developing quantum applications, perhaps with AI in mind. However, what we've started to do recently is look the other way around and look at using recent advantages in generative AI in terms of our own workflow. So we've been building, so we have a small team internally that has been building, agents for scientific workflow. So we've been trying to eliminate some of the major barriers that you have in terms of getting reliable results out of them. Of course, language models are not a great way to do science in general. You can start to get some better results with RAG, where you're pushing appropriate material into the context window, but there's still issues with hallucination and with attention. But we're actively experimenting with this and seeing how far we can go in terms of using this for our own development, both in terms of code generation and in terms of solving more mathematical problems. So that's it for me. Thanks very much.
Yes, thank you very much, Joe. Thank you very much, Joe. Any quick question from the audience? Yes, Stefan. Wait, I'll bring you the mic so that the people on Zoom can hear.
So when you showed the compilation of the basic code to some hybrid model, so how detailed is the cost model that the compiler is using to decide whether it should generate quantum or stay with the classical code?
Sorry, I can't. Can I use the pointer? Thanks. So let me. So this isn't a basic language. This is MATLAB. So this is a subset of MATLAB, and this is what we're going from. In terms of how we work, we have not. I mean, we're not putting a big weight on constants at the moment. They're very dependent on the different quantum computers you have, the different architectures, the gate times for the different models, the connectivity of the models, the overhead that's going to come in from error correction of fault tolerance. We don't yet have systems that could execute this program, for example. You need a more complex system than is currently available. The cost model, though, is pretty straightforward. So a lot of work that gets done, particularly in industry on quantum computing, focuses on things like variational techniques, these NISQ algorithms. And I mean, I'm very opinionated on this, but my view is that there is no future there, that they do not really have provable advantages for most problems. With that in mind, the way we try to structure this is we try to do everything in a way that exactly replicates the performance of the program. So this fine minimum, we're not going to do it in a way that calls an optimizer that may or may not work. We need to exactly find the minimum. So whenever we do any replacement on the code, we need to maintain all the side effects. We can't change what the code does. And of course, that's something that happens a lot with most kind of applications of quantum computing today, or POCs of quantum computing. People try to replace an optimizer with QAOA or VQE or something like this. And we don't do that. Instead, we try to replace it with algorithms that we have provable performance bounds on, so we know exactly how long they're going to take. In particular, things like if you have a for loop and there's an if statement inside it, we can accelerate that directly by using a quantum algorithm we have for linear search, and we know exactly what the performance of that is compared to the classical one in terms of the number of times the code within it needs to be called. Now, how much we should weight a particular instruction on a quantum computer versus a classical computer, there is no known answer for that today because we don't have production level quantum computers. But that's where we are. So at the level of number of instructions, yes, we can do very detailed resource counts. We can decide pretty accurately, and the constructions are all such that they never give worse performance, or never worse than a factor of 2. Yeah.
Yeah. As I always this product is something that gels very well with our overall strategy, and we are very keen to look into tapping onto your to further accelerate our research and also our developments. So, for example, the example that I showed you earlier on about this hybrid cluster, hybrid CFD solver might be a very good use case for us to explore further. So, to that front, yeah, of course, for our case, we are open with both the variational and also the non-variational algorithms for that case, especially for the linear solvers that specifically solve for the Poisson equation. So, my question is that concerning your current capabilities and the features available in your, for example, Helium and also your high-level languages, especially for this one, what's your perspective if we tap on our hybrid solver scheme with your tools, and how does that will be enable some of the more sophisticated scenario, especially, for example, we want to look into how does a given a different type of quantum computer systems, how that will be factored into the system size that we'll be able to solve via this solver.
Sure. So, I mean, basically where we stand today, I should say the high level stuff where it's algorithm generation, that's still R&D, that's not productized. It's not integrated into our software. So it's not really available for use. It's still, there's still a lot of work that needs to be done, particularly to connect the output. I mean, I guess I showed you it identifying the quantum algorithms, but that was in MATLAB and we can compile from C. And so there's like some bridging we need to do. From Helium all the way down, that works now. We have, we're onboarding external users onto the system more or less at the moment. In terms of what's possible in that, you know, I can't really speak to the algorithmic performance because it depends on what the algorithm you implement looks like. So it's a kind of case of garbage in, garbage out, right? What I can say is that when we talk about compiling from C, we see enormous advantages over hand-built circuits for the most part. So I've shown some numbers previously on doing this for things like the computing e to the minus x and things like this, where, you know, state of the art a couple of years ago, that if you want to do that to 21-bit precision, it was taking 15,000 Toffoli gates. We can do it in 140 or something. So from that perspective, we get much better performance over what you would construct by hand, unless you spend an extraordinary amount of time optimizing your hand-built circuits. We have been experimenting with different optimizers on the way down. The optimizer is more or less disabled in the system at the moment. So the generated code has some redundant operations in it. It's not all that well optimized yet. So it really depends what you want to develop. What I would say, however, is there's unique capabilities in the language that just aren't possible in other high-level languages, particularly in terms of expressing non-circuit computation. So if you look at things like the distributive eigensolver and things like this, you just can't express them directly in most programming frameworks. And that's something that we open up, and we, even for a system that does not support non-circuit computation, so you want to run it on an IBM system, something like that, we automatically construct a hybrid program behind the scenes where it will unroll the circuit as far as it can, run it up to that point, go back, try to compile it again based on any results it has to that point, or if it needs to acquire information from the user, and go back and forth in a way that is completely hidden from the developer or from the user. It's just a single API interface, and it's running all of the post-selection, all of that behind the scenes to make it run directly from end to end. Although, of course, the more post-selection that happens, the more runs are required, and it takes longer time and costs more to run on hardware. But yeah, that's basically it.
So I think in this sense, interface
can we keep this for later?
Yeah.
Okay, thank you very much. Sorry. Sorry. Thank you, Joe, again for your nice notes. So in the interest of time, we're like 19 minutes late, but it's okay. We still have time. Now we go for a break. It's supposed to be until 3:30, so we'll go until 3:40, so that we have at least 20 minutes for a break. And then we come back, And then we will be divided. It would be great if you could divide yourself in 5 tables. I will ask maybe some people to help me anchor those tables. And then we can have a discussion later on focusing on, how AI for science and hybrid quantum computing and quantum computing in general can work together. Okay? Thank you very much. Enjoy your break. I can see you at 3:40. Thank you, everyone. Hello, 4:40. So, sorry, was it shocking? Is it? Okay. Let's take, yes?
Which clock you're using for 5 minutes.
Don't worry. It's not an atomic clock. Okay, anyway, so I was sitting at the table, learned quite a lot of things, and then I'm sure there was good discussion at the other table. Let's, without waiting any time, we asked them, because I was here, so I already know from them, if you don't mind, you can start 5 minutes, through 5 minutes, not the speaker session before 5 minutes, if possible. No, but if you, of course, have interesting things to do and need like 6-7 minutes, it's okay. We'll accept it because we're interested. We're here to learn. Right? We can stay a little bit longer. It's not too bad. So maybe we start here, if you guys don't mind. Maybe who wants to share something? Who will be speaking for you? You haven't decided?
Sure.
Joe, okay.
I have some notes, at least from what we discussed.
Thank you, Joe.
Okay, thanks. So we essentially combined 2 different tables. One looking at applications or near-term applications for AI and quantum, and the other one looking at bottlenecks to applying AI to quantum. A lot of the time, at least the initial period of the discussion, was focused on talking about AI for quantum and how AI can be applied to help with developing quantum computers and so on. The discussion was initially around things like better decoders for error correction. So although we can do decoding for error correcting codes of a small size on a small number of qubits, as you get to larger number of qubits, you need to be able to do that error correction in real time so that you can correct the error while the system's still alive and the error is still accurate. But it becomes harder and harder in terms of computational problems. And this varies with each new code as well. Every time someone develops a new code, the decoders potentially need to change and so on. We also touched upon optimal control, so designing the pulses and so on to control systems and characterize them. We talked about potentially using AI for designing ansatz circuits for variational techniques, and some results that I believe have already been obtained in that space. We talked about whether this can be done more generally for quantum algorithms, and whether you can design maybe the more structured algorithms like Shor's algorithm using machine learning techniques. And I think we maybe came to the conclusion that there's just not enough training data to be able to do much in that direction at the current time, although there might be some instances where there are tunable parameters that ML techniques can be applied to. The other side, we talked about, quantum for AI, the different kinds of techniques for that, as well as in relation to applications. So one of the bottlenecks to getting to machine learning for, let's say quantum algorithms for machine learning or AI is noise in the quantum system. So current systems are really noisy. The variational techniques, it's very difficult to analyze. So being able to prove an advantage on those is difficult. And if we can get into the error-corrected domain, then we know that there are algorithms that should show a speed up over classical algorithms for implementing the same models. But a big bottleneck we have there is the lack of quantum random access memory at the moment, which makes it very difficult to load in large amounts of data. We talked a bit about optimization problems and whether there were near-term prospects for that. And I think at least where we finished up was talking about whether chemistry was maybe a more realistic near-term goal for quantum computing applications. I think that's it for us. Thanks.
Thank you. And everybody at this table. Okay. Do you guys want to go? Who is your representative? Okay. Thank you, Manas, then.
It would be very quick because probably Joe covered most of them. I don't know why it's the same topic. So we could not disagree with what you said, most of these places. But however, I think we have some few new things probably is we think AI for materials, which is already in Singapore, there is a consortium. If we could get access, perhaps this is an avenue where we can explore what are possibilities for device making in quantum. Yeah, that's one thing. The other thing, again, coming from more fabrication side, is we often see to make devices better and better, there are a lot of data produced, but if AI could be put into practice to see how to optimize those, yeah. But again, this requires credible data, and we were thinking if there could be a cloud where people can just plug in their data or put in their data and collect it over time, yeah. I think for error corrections and error mitigations, we probably are on the same page. Then what do I have? Yeah, platforms. We are supposed to talk about platforms, and one thing came out is photonics has one advantage being both classical and quantum in terms of classical processing. So, but then again, there is also a counter argument that, of course, the classical one you can use with any other platforms, and currently all platforms are in the similar stage, a little bit ahead or behind in each. So you can still use the photonic platform for classical processing, but the quantum platform can be any. Yeah. I think anything did I miss, or there was this regenerative circuits, but I think that's already covered in before by Joe. Yeah.
Thank you, Manas, and everybody at this table. Thank you very much. The last table, Pan Feng is here. Okay. Thank you.
Yeah, our table mainly talk about the algorithms about AI for quantum computing and quantum computing for AI. And we all agree that we only have limited number of qubits in the current stage, and we need to seek to the hybrid quantum computing approach to help us solve problems. Yeah, so for the AI for quantum computing, so we are all complaining about the current noisy quantum hardware, which basically give us nothing about the information. So what we want to do is to firstly use the reinforcement learning for the error mitigation. Maybe through one is modeling the noisy state, and to help to get help from the AI to tell us what is happening inside of the noisy state. The second one is we may need reinforcement learning to tell us how to do transpilation by decreasing the number of gates and to decrease the effect of noisy. And the second approach is that we could use neural state to do the simulation of the quantum computation models. And also we could use neural state to modeling the quantum dynamics to help us to understand the physics things behind the quantum computational model. And the second one, we should be talking about the quantum computing for AI, but since we are basically all doing some quantum many-body system research, so we basically coming up with some ideas about quantum computing for quantum many-body systems. So the first one, maybe we can achieve quantum advantage is that we can encoding the Hamiltonian into the quantum circuits and let the quantum simulation to tell us about the properties of this Hamiltonian. That is one big hope for achieving some quantum advantage using the quantum circuit model. And the second one is that maybe quantum computing could also help us to generate valid Feynman paths to avoid the sign problem of the quantum many-body physics, because it utilizing the superposition nature of the quantum states. Yeah, that is all of our discussion. Yeah, thank you.
Thank you, Pan Feng. And everybody at the table. Okay. So then what I'm asked is to wrap up, but I think there has been already very good discussion. So maybe first of all, I would like if any of you has something very present, things like, oh, this has not been said, and I think this is important. And anybody wants to say something else? Yes, please. Or ask some questions.
You mentioned the photonic aspect, and we had a good presentation from Kwek on that. So that relates also to the local capabilities. Maybe since he's not here, you should ask him to give some input on that part. Yeah.
Yeah, and then one of the tables that was not formed was the table of local strengths and capabilities, and which maybe we have not touched. But I understand we have superconducting qubits, we have trap ions, we have photonic, and we have NV centers as well. Okay, although they're not used for quantum computing, but for sensing at the moment, for what I understand. And so these are the platforms that I think are currently present in Singapore. Neutral atoms, of course. Yeah. Oh, of course. Yeah, trapped Rydberg. Yes. Very nice. And then there are people who are investing significantly effort in hybrid, and then also in fault tolerant, and then that seems to and applications. I know people are working in quantum chemistry, correct? Yeah, for example, and then there are people who are trying to work with finance and I think optimization in general. This covers quantum many-body physics, indeed, myself included. Okay, fair enough. Okay, thank you, Pinaki, and Pinaki too, of course. Am I missing something important here? Quantum machine learning, of course. Okay, so I will keep this in mind. I may contact you before 15th of June. Some of you, to have some, if I need some clarification, some things for the report that I have to put together. But yeah, overall, I hope this was a fruitful meeting for you. You got a chance to meet some people you have not met before, and this may be at least bring some good collaborations for the future, ideas and new things. I hope. Yeah, and thank you very much for coming. This is I was confident that I could run this workshop because I thought people would come. Okay, because I thought the community here is a nice community and very interested, invested, and exciting. So thank you very much. Okay, thank you, and thank you, Hans. Okay, thank you, Hans, for organizing so many things. So thank you.
Maybe one suggestion is
Sorry.
Maybe one suggestion to our artists to do it again.
Yes. Okay. Noted. Okay, good. Thank you very much. I think there is more food out there if you want to have more food, if it wasn't enough for today. Okay. Okay, thank you.